Students, now we have another property of DFT, which is multiplication in time, which is also known as modulation property. As we know that modulation simply refers to the multiplication of the two signals, and those signals are in time domain, right? So whenever the two time domain signals are multiplied, what is the DFT of those multiplied signal? So that is about the multiplication in time, also known as modulation property, right? So if I consider the two discrete sequences x1 of n and x2 of n, x1 of n and x2 of n, and you multiply both the sequences and then take the DFT. So what is the DFT of those multiplied signal in time? So that we have to understand in this property. So let us write the statement here. So if x1 of n and x2 of n be the two time domain sequences, and x1 of k and x2 of k are the DFTs of sequences x1 of n and sequence x2 of n, then if I multiply these two time domain sequences, that is x1 of n and x2 of n, right, and if I take the DFT of these two, if I take DFT of the multiplication of these two sequences, the result will be 1 divided by n into the circular convolution between the DFT sequences of x1 of n and x2 of n. So what is the circular convolution representation? So it is a circular convolution, n point circular convolution between the DFTs of x1 of n. x1 of n DFT is x1 of k, and the DFT of x2 of n is what? x2 of k, right? So the DFT of the product of two time domain sequences gives the circular convolution of the DFTs of the two signals x1 of n and x2 of n multiplied by 1 divided by n, where n is the number of samples in the sequences x1 of n and x2 of n, right? So now let us prove this one. Let us see the proof of this property. So now let me start with the definition of DFT, right? So DFT of x of n we know, which is given by summation n is equal to 0 to n minus 1 x of n multiplied by, that is complex function total factor w kn, right? So now what we have to prove is, we have to prove the DFT of the product of these two sequences is equal to 1 divided by n times x1 of k circular convolution with x2 of k, right? So now let us write x1 of n and x2 of n in place of what? X of n. So that is the multiplied sequence. So DFT of the product of two sequence will be x1 of n. It is simple multiplication. x2 of n is equal to summation n is equal to 0 to n minus 1. So here I will write x1 of n as x1 of n into x2 of n, right, multiplied by wn kn, right? And here to simplify further, in order to get the required proof, keep one of the input sequence as it is and the another sequence you defined using IDFT definition, right? So here what I am doing is I am keeping x1 of n as it is, so my summation is as it is, n is equal to 0 to n minus 1. We'll keep x1 of n as it is, and using IDFT definition I will write down x2 of n, right? So using IDFT, how we write x of n? X of n is equal to 1 divided by n, summation k is equal to 0 to n minus 1 x of k, and here it is wn minus kn. Understood? So here I will write x1 of n as it is, I will keep, and I will write x2 of n using IDFT equation, that is 1 divided by n summation. So instead of k I will use another notation for summation L is equal to 0 to n minus 1. So here it becomes x2 of k, because the DFT sequence of x2 of n is x2 of k, and here it is wn minus k into n is there, so in place of n I have to take L, right? So in place of k I have to take L here. So wn minus k means in place of k I have taken L, so it is minus L into n multiplied by this term, that is wn k times n, right? So let me take this 1 divided by n outside, and also this summation, that is L is equal to 0 to n minus 1 outside. Then next I will write this, one more correction, so this becomes x2 of L, and here I will write x2 of L. Then I will take this summation inside. I am just interchanging the position of summations. Next n is equal to 0 to n minus 1, and this x1 of n, and then this wn, I will combine both these functions. Since in the power of these two n is common, so I can write it is k minus L into n, right? So if summation n is equal to 0 to n minus 1 x of n into wn kn, I can write this one as what? X of k, right? In the same, if I replace k by k minus L, then the same thing can be written as what? X of k minus L. So therefore this summation term can be written as, so here I will write 1 divided by n summation L is equal to, so just I will write down here 1 divided by n summation L is equal to 0 to n minus 1 x2 of L, and this part is what? X of, that is x1 of k minus L, right? And if you see the definition of circular convolution in time, right, it is 1 divided by n. So summation L is equal to 0 to n minus 1 x2 of L, and here it is x1 of k minus L. I will take one more step. I will write like this: L is equal to 0 to n minus 1 capital x1 of k minus L, and here it is x2 of x2 capital x2. So this is capital X2 of L, right? So what is this? This is nothing but the circular convolution of the two sequences, but in frequency domain, right? Instead of lower case small x, we have capital X1 and X1, means they are the DFT sequences. Therefore it is 1 divided by n and here it is circular convolution between x1 of k and x2 of k, right? That is equal to dft of x1 of n multiplied simple multiplication with x2 of n is equal to this one. So this is the required proof, right? So whenever you multiply the two sequences in time, its DFT is equivalent to the circular convolution of the same two sequences in frequency domain multiplied by 1 divided by n. This property is known as modulation property. In the next video, we will discuss one simple example on this property.